Good afternoon. Hi, very happy to see all of you here. My name is Oleg S, and I work for the GraalVM team at Oracle Labs at Oracle. And today we're going to talk about the GraalVM native images. And I try to cover the most essential parts, and most importantly, to show the tool in action, what it can do, how you can benefit from it, and maybe a little bit of configuration, this and that, in a more practical approach rather than other sessions. So yesterday we had a deep dive into everything you need to know about GraalVM in the morning. How many of you have been there? Quite a bit. Oof. Okay. There will be some repetition, but repetition is very good for remembering things, so I hope you'll stick around. Right, so GraalVM native images explained. Some disclaimers about the presentation, very important. GraalVM itself, it's a rather large project. It can do many things. The most important things and the goal for GraalVM is to run programs more efficiently, faster, if you wish, and also to enable the additional productivity for developers by being more flexible, by enabling using your applications in different environments, like maybe cloud deployments or serverless platforms, and so on. So GraalVM has this noble goal of making software more efficient and people more efficient. It's all about efficiency. All in all, if you want one short, visible presentation about what GraalVM is, this is this slide. GraalVM is a high-performance polyglot embeddable runtime virtual machine for different languages. Currently, we support the JVM languages. We support Ruby, R, Python, JavaScript, of course, and some native languages as well. And we can run all those languages, programs written in those languages, in different environments. We can run it in a JVM. We can run it in a Node.js application. You can embed GraalVM into your Java or native applications, or you can compile some programs ahead of time into the native executable for the platform, the thing that you double-click and it runs by itself without any additional environment around this. And today we're going to talk exactly specifically about this mode of compilation ahead of time of programs into GraalVM native images. So if you are interested in GraalVM in general, there are a number of goals that GraalVM tries to reach and a number of things that GraalVM offers to you as developers. But we're going to talk about the low footprint ahead of time compilation mode for JVM-based languages called GraalVM native images. Right? If you want to replicate some demos from what I'll be showing, or if you want to play around with it, you're in the luck. You can just download GraalVM. You can just go to graalvm.org/downloads, or just Google the download, and you can get GraalVM in two flavors: either a community edition, the open source project built into a binary that you can download and run, or there is an Oracle GraalVM Enterprise Edition, which is a product, and which you can get from the Oracle Technology Network for evaluation and try it, or you can use it on the Oracle Cloud for free. So it's fairly easy to get started. Let's talk first a couple of slides before we get to the demos and start building native images. When we talk about performance, right, we talk about a number of dimensions for what we mean when we say performance. For some people, it's startup. For some people, it's a peak throughput. For some people are really, really careful about the tail latencies, not to have any request go unanswered in a short period of time. And there is a trade-off normally, right? So we can optimize our programs for different characteristics at runtime. If we care about throughput or the smallest tail latencies that we want, we probably would like to run in a JIT mode, right? JIT is a just-in-time compiler that can compile your code at runtime, that has the best view into the system, into the code that is running, into the data that is flowing through this code, so you can make the best decisions at runtime, just in time, for optimizing the code. That's how it will probably achieve the peak throughput the best. However, that approach has some downsides, and for example, to achieve this peak throughput, you probably need to warm up your application quite a bit. So your startup time will probably suffer a little bit. Also, to compile things at runtime, in a just-in-time thing. You need some infrastructure for that, right? You need to bring a compiler with you into the runtime. You need to allocate some data structures for managing the code that you want to compile. You need to have some metadata. So your memory overhead for the program could be much more significant compared to the solution where you compile everything to the binary and then you don't have any compilation facilities at runtime available for you. Right. So, luckily, GraalVM can do both. GraalVM can run in a JIT mode within a JVM, right? And you can use just a Java utility from the GraalVM distribution and run your application normally. Or you can feed your application classes and jar files into the native image utility from the GraalVM, and it will provide a binary for you. What happens when you build this binary? What happens when you run native image my main class? Very interesting question. And what happens is the following. The classes of your application are being analyzed. So native image gathers all the classes that it thinks will ever be executed in your application. So it consumes your application, all the dependencies that you have, right? All the classes from the JDK class library, and then some classes from the runtime bits that are necessary to run in the final image, like the garbage collection. You would write your programs in Java, and you write them with the assumption that the memory is infinite, right? Because the garbage collection will always create some free space for you to allocate objects. And it would be a shame if this property will not hold after the compilation ahead of time, right? So the result has to run with some sort of garbage collection, and that implementation of the garbage collection comes from the project within GraalVM, codename Substrate VM. If someone mentions Substrate VM to you, you know what it is. Right, all those Java classes, and this is normal Java classes, right? It's Java code. All of them are analyzed and initialized a little bit, and then they are compiled. The JVM bytecode is compiled to the native executable. Excellent, yes. So the analysis that is going on is we figure out which methods and classes and fields and other methods and classes and fields are reachable in the application, what code is actually will be running, because there could be some parts of the code that will never run, right? If your application doesn't do anything with currencies, for example, right? Maybe you don't need to include the currency-related classes into your Java application. If your application doesn't do anything with XML parsing, right? Maybe you don't need to include the facilities for the XML parsing into your application. Sounds reasonable? Sounds reasonable. But in order to know what to include or not, we need to do the analysis. Afterwards, those classes are initialized. They are prepared for the runtime. And then the objects and the heap situation is snapshot and put into the resulted images as well. So if you have some data structures that you can initialize eagerly at the compilation phase, that would be initialized and written out in this final object form. So you don't have to do that again. So after that, the classes are compiled, the methods are compiled, the heap is written down in the executable. It's all wrapped into the platform executable, the ELF format, and the result is written out to a file. How can this work? This works with one very necessary assumption. The assumption is that all the bytecodes, like all the code that is gonna ever run in your application, is available at the image generation time. This is very important for two reasons. First, it enables us to make more aggressive optimizations while we compile ahead of time, because if we know that there will be no changes, we can assume that there will be no changes. And when we assume that there will be no changes to the structure, to the class files, or to which methods are calling which methods, right? We can inline things more aggressively, and we know exactly which methods will be called. So there are no changes in the class hierarchy, for example, so there couldn't appear another polymorphic call somewhere, which is very important. And second, by using the closed world assumption, we can make sure that there are no bytecodes that need to be loaded at runtime. that we can exclude all the compilation facilities from the runtime in the native image. So that also poses one of the obstacles on the way of compiling programs into the native images, naming there are several dynamic parts to typical Java programs. For example, you can use reflection, and you can use that dynamically at runtime. Right? You can construct method calls, or you can access fields of objects at runtime dynamically. And no static analysis can figure out what you're going to do. You can literally write a program that will take user input, and based on the user input, execute reflectively a method. No static analysis can figure that out, because there is essential parts of the input are missing until runtime. So the closed world assumption kind of poses a challenge for that, and we'll address that in a moment. Now, one important thing of the snapshotting the heap is it's also possible under the closed world assumption, much better than without. But what it gives you the ability to configure your application to a certain extent during the generation phase, and then use it at the startup without any initialization happening, right? So you can literally, as a developer, you can control the point up until your application will be initialized when you're using native image, which gives you great flexibility. Might be not super straightforward, but could be a great advantage. So if you want to jumpstart your project, if you want to build native images of your projects, you would need to have a couple of options. And here's a short summary. We're going to go into the demo mode, and I'm going to show you building several images and talk about that. And then we come back to this, and hopefully we understand better what those mean. Right, so let me go. What happens? Right, no, wait. I need to edit. This is mirrored now, right? My screen is black. Excellent. My screen is not black. Right, I have my GraalVM here. I have my GraalVM 19.2.0.1 downloaded. It's not the latest, but it works for me. So you get something similar if you go to the website and download the binary. If you look at the bin directory here, we have the native image command available here. I installed that with the GraalVM updater utility, GU, and you will have to do that as well. So after that, you prepare that, and you can run native image, and you can run it with different options, right? Oh, wait, help. Right? You can see that there are plenty of options that you can configure just from looking at the help. However, native image, in a nutshell, it takes your jar files and it outputs the binary. So let's look at the sample program. Let's look at the simple program that doesn't do much. Right? It's a Java program. What it does is not, strictly speaking, important, but what it does, it just takes some input and walks the file path. Right? Very simple program. Just to show you the native image tool in action. Native image, and I will feed the class. First, I will compile the class, right? Java C, list dir Java. I will compile my application, right? And then you can see that we have the list dir class here, just created. And I will feed that to the native image. And it will take a little bit of time, and you have to be prepared to that. Why it takes a little bit of time? First, because this machine is not the most powerful machine in existence. It's not even the most powerful Mac in existence. And second, because we need to do the analysis. And you would think like, oh, how much analysis time they need to do? It's one class. But you have to understand that one class is actually pulling the whole JDK standard library with it, right? Because it can use all other classes. It uses the file class, and it uses the pass class, and there are plenty of classes that it can use. So what it did, it created a list dir executable for me. I'm going to run this. If I run this, it walks the file path, and it outputs some information to me. I can give it a random file path, and depending on the input, it produces different output. No cheating. Actually, I can show you the same with the Java version. Right? You can even see that the amount of bytes that it computes is the same. Would be a shame it would be if it would be different amount of bytes. But the difference here is that if I do what I do, if I time my command here, you can see that it runs in no time whatsoever. One reason for that is it doesn't need to initialize the JVM and do the class loading and do the class verification and then trigger the compilation facilities for the just-in-time compiler or anything. So it's instant. Now, another thing that I wanted to show you is this. I'm going to run this visualization created by Thomas Wurtinger, actually, who is the leader for the GraalVM project. And what this visualization will do, as soon as my Python will... Oh, it's actually serving something. Sorry. Localhost 80,000, right? What I can do, this is the map, this is the image of all the classes that went into the Hello World native image, right? You would expect that, oh, why? It could be just one class, right? Actually, after all, we had one class in our Java application. But it's not. These are all the classes. I think the color represents a package, and every rectangle is a class, right? So we can see that there are quite a big chunk is Java util, which is the JDK classes which are used or potentially can be used from our application. There is this blue bit. This is the implementation of the garbage collection coming from the GraalVM project, right? Because we would like to run our application with the garbage collection. There are some Java util regex, even though Hello World doesn't usually do regex. There is some math. There are some Java.NET. There was also some formatters, like a simple date formatter or the decimal format. Do you know where this is coming from? Who can guess where this is coming from? Nobody? I think it's because your application can throw an exception at any time. And when you have the exception, it has to be able to print itself. And when you print itself, it has to support some formatting options for different things. So it pulls that code in through that facility. Well, you wouldn't expect that, but it does that. So what I wanted to show here is that there are quite a bit of Java, quite a bit of code goes into the native image. But at the same time, the result is actually, let me stop this Python server. The result is not very large. So if we look at the list dir here, it's what, 8 megabytes. I think it's significantly smaller on Linux. And for the Hello World, actually, if anyone measures, I think the native image size, the binary size, is about 2.6 megabytes or like 3 megabytes. Allegedly, I didn't check recently, but it's small, right? And you can, it's a native binary. You can ship it in an empty, from scratch Docker container. Normally, it's linked against the operating system, like glibc and so on. But you can also try static building, right? You can link into the minimal Docker container, and it will run there without the dependency on the JVM, right? So we can limit your deployment unit size as well, right? So this is the native image in a nutshell. What else it can do? Remember I said that you have to configure reflection and things, right? Because so those dynamic features are not, they cannot be analyzed statically. And so they cannot work out of the box. Let's see how it goes. I have this sample program here. It's called Hello Reflection Java. What this application is doing, it takes the arguments from the input, and based on the arguments from the input, it will invoke a method, right? So it will find a method based on the argument, and it will invoke it. So if we do Java C hello reflection, and then we do Java hello reflection foo, we get running foo, right? If we do Java XYZ, whatever, we get a no such method exception, right? Normal behavior. Right? What will happen if we try to feed this application into the native image? Who knows? 2 people. Right. It will yell at you. It will yell at you, and then it will go into the fallback mode, and it will still create a thing that will run, but that thing might not have the performance characteristics that you would like. So what you need to do to enable this, you need to build the native image with the flag no fallback. And then the compilation will yell at you with an error. Let's see. Right? So our application uses reflection. Native image cannot handle reflection without additional configuration. Right? It just impossible. Right? So what it should do, it should tell us about an error. Allegedly, apparently it does it at runtime. Surprisingly. If you don't specify no fallback, it will yell at you at compile time. However, if we run this is a proper application, right? If we run this with hello reflection foo, it will fail with a no such method. But you can see that in the actual Java application here, we have the foo method, right? So this is not what we want. So what we want to do, we want to configure reflection to include the necessary methods and necessary code in the final native image. How do we do that? By providing a configuration file. It's a JSON file, right? You can write it by hand. What you else can do, which is how we think you should do this, you should run a Java agent, and you should run your application using normal JVM, using normal Java process with the native agent, and you should record the configuration for your native image. So if I run the following thing, tracing, right? I will run the following thing. I will enable a Java agent, and I will tell it that this is going to be its native image agent, and the output for this will be a directory here. And I will run hello reflection application, and I will give it foo and XYZ as an input, right? Run Java tracing. We run this. Inf, what? Let's try it again. Right, excellent. We run our application, we run method foo, and we couldn't figure out how to run method XYZ because there is no such method, right? And there is actually no such method in our program. What we created though now, we created the configuration for the native image. So if we look at the meta-inf directory, native image, reflection configuration, we can see that there is a JSON file that says, on the class hello reflection, we will reflectively access method foo without parameters. So if your application uses reflection, that is not an obstacle for using native images. You just need to configure that. You don't even have to configure that manually. You just use tools in action to provide this configuration for you. So now we can build a native image, native image of the hello reflection, and since the meta-inf/native image directory is right here on the class path, the native image tool will find the configuration, and it will do the thing, and it will include the necessary parts for the reflection on the class hello reflection for calling method foo in the image. And I can do the hello reflection foo, and you can see, and I can time this. Let me time this. See? Reflection doesn't slow down the invocation of this binary whatsoever. Right, so this is how you configure reflection. The same way you configure proxies, you configure JNI, you configure what other dynamic features are there. You configure the whole thing that is necessary for configuration for native image. What else you can do, that configuration needs to be on the class path when you generate native image. What you can also do, you can embed that configuration into the jar file for your application. Right? Literally, you put it inside the jar file into the meta-inf/native image directory, and it will be picked up. With this approach, you can build non-trivial applications using native image into native images. Most probably, how many of you write web applications for a living? Most of you. What do other people write? Spreadsheets? It's important. It's very necessary. But just if you don't write applications for a living, then native image tool might not be directly improving your life. However, I digress. That might not be true as well, depending on what actually you're doing. I will look at this application, which is a web application. It's a Micronaut application. There was a deep dive into Micronaut yesterday. I appreciated and enjoyed that session very much. So here's the Micronaut application. This application is dealing with quotes from smart people or some unknown quotes and some just maybe just quotes. Let's not go deeper into that. What we will do, we will build this application into a native image of itself, right? It's a web application. I will run it. I will actually run it. Let me run it. Java -jar build libs jar file, right? I run this. This is an application. It should run. Hopefully it will run. It ran yesterday. Yeah, it's a port. Right. Wait. Quotes. Note that this was not even the native image running. This was the Java process, so you cannot blame native image for this. Let me kill this. 364, right? And then we'll run this application, and it should run. Yes, it runs. It runs, and it's an application. And if I look at the 8080 quotes random, what do I get? I get a quote. I get another quote. Yeah, see? The other 19% is debugging. Interesting. So because things don't go right. And we should know that. Right, so it's a small application. There is no point in playing with it very long. I can run it, and I can build a native image on it. So the thing is to notice here is that the Micronaut application, since Micronaut is supporting GraalVM native images as the deployment platform, it includes some native image configuration in the meta-inf directory here. Right, and this configuration instructs native image to include some files. Files we cannot include by default as well, right? Files cannot be statically analyzed which files need to be included because it's not Java code. So you need to configure that. And it provides some properties. So when we build this application, we just say native image, build this application, and we pass all the jar files there, right? And it's all good, and it all runs. And I pre-build this application because it takes a few minutes on this. And I can run it, quotes app, and it runs. And I can run it again, and it runs in a ridiculous small amount of time. So it starts in no time whatsoever. It's actually not just starts in no time whatsoever, but if we test the startup, if we start the application and ping it with a request to see how much time it takes to respond a request, right? How much time do you think it will be? Who thinks it will be like a second? Right. It takes something like 70 CPU milliseconds. The whole CPU time that went into serving a request and giving a quote, hopefully inspirational to us, is 70 milliseconds, which makes GraalVM native images a very interesting target for all your cloud deployments where you auto-scale things automatically because their startup is very important. And even more importantly, for the deployments where your memory consumption is paramount. If we run this quotes application, right? This is native image, and let's ping a couple of quotes, right? We use it extensively, right? Sometimes not all applications are seeing this usage even in an hour, but if we look at the memory consumption here, you can see that our application here just takes a few megabytes of memory. You can serve your microservice for the few megabytes of memory at runtime, which is incredible. And you can do more things. Let me show you. There is not much time here, but if you look at the native image, and then you do what? Expert option help? Wait, help? What do you mean? No. Native image help, right? And we will look at the thing called expert options. Wait. No. Help extra. Yes, I think so, this. Native image. Help extra. I would just want to appreciate the amount of options that that native image has available. Just takes some time to process, and it's a lot, right? You can configure almost anything, like regarding how the EAT compilation works or anything. So this might be a little bit too much because you don't want to configure everything. So what you do, most normally you would use a framework that supports GraalVM native images out of the box. So what you can do, you can configure reflection, you can configure class initialization, and you can debug things. But what I want to show is that there are a number of frameworks that support native image. And when they use GraalVM native image, the startup time for them becomes absolutely negligible, very small. And the memory overhead reduces by several factors, right? We are working, by we I mean GraalVM team, are working on improving the peak throughput and latency numbers for the runtime, for the native images specifically. And you can download and use GraalVM, and you should try this. Native image can be put in production. I know of several companies who use native images. One of them, I think, is Devox. There was a session about how they build the speakers photo image recognition application and deployed native images somewhere in the cloud. So if you're interested, there are people in the ecosystem who are having some experience with native image. So what you can do, you can try it. You can come to us with the feedback. You can tweet at us. And most importantly, you can build your applications and run them more efficiently in the cloud. Thank you.